Infrared is invisible radiant energy, electromagnetic radiation with longer wavelengths than those of visible light, extending from the nominal red edge of the visible spectrum at 700 nanometers to 1 millimeter. Most of the thermal radiation emitted by objects near room temperature is infrared. Infrared radiation was discovered in 1800 by astronomer Sir William Herschel, who discovered a type of invisible radiation in the spectrum lower in energy than red light by means of its effect on a thermometer. Slightly more than half of the total energy from the Sun was eventually found to arrive on Earth in the form of infrared. The balance between absorbed and emitted infrared radiation has a critical effect on Earth's climate. Infrared energy is emitted or absorbed by molecules when they change the rotational vibrational movements. Infrared energy excites vibrational modes in a molecule through a change in the dipole moment, making it a useful frequency range for study of these energy states for molecules of the proper symmetry. Infrared spectroscopy examines absorption and transmission of photons in the infrared energy range. Infrared radiation is used in industrial, scientific, and medical applications. Night vision devices using active near-infrared illumination allow people or animals to be observed without the observer being detected. Infrared astronomy uses sensor-equipped telescopes to penetrate dusty regions of space such as molecular clouds, detect objects such as planets, and to view highly red-shifted objects from the early days of the universe. Infrared thermal imaging cameras are used to detect heat loss in insulated systems, to observe changing blood flow in the skin, and to detect overheating of electrical apparatuses. Thermal infrared imaging is used extensively for military and civilian purposes. Military applications include target acquisition, surveillance, night vision, homing, and tracking. Humans at normal body temperature radiate chiefly at wavelengths around 10 micrometers. Non-military uses include thermal efficiency analysis, environmental monitoring, industrial facility inspections, remote temperature sensing, short-ranged wireless communication, spectroscopy, and weather forecasting. Definition and relationship to the electromagnetic spectrum. Infrared radiation extends from the nominal red edge of the visible spectrum at 700 nanometers to 1 millimeter. This range of wavelengths corresponds to a frequency range of approximately 430 terahertz down to 300 gigahertz. Below infrared is the microwave portion of the electromagnetic spectrum. Natural infrared. Sunlight at an effective temperature of 5780 kelvins is composed of nearly thermal spectrum radiation that is slightly more than half infrared. At zenith, sunlight provides an irradiance of just over 1 kilowatt per square meter at sea level. Of this energy, 527 watts is infrared radiation, 445 watts is visible light, and 32 watts is ultraviolet radiation. Nearly all the infrared radiation in sunlight is near-infrared, shorter than 4 micrometers, on the surface of Earth, at far lower temperatures than the surface of the Sun. Almost all thermal radiation consists of infrared in mid-infrared region, much longer than in sunlight. Of these natural thermal radiation processes, only lightning and natural fires are hot enough to produce much visible energy, and fires produce far more infrared than visible light energy. Regions within the infrared. In general, objects emit infrared radiation across a spectrum of wavelengths, but sometimes only a limited region of the spectrum is of interest because sensors usually collect radiation only within a specific bandwidth. Thermal infrared radiation also has a maximum emission wavelength, which is inversely proportional to the absolute temperature of object, in accordance with Wien's displacement law. Therefore, the infrared band is often subdivided into smaller sections. Commonly used subdivision scheme. A commonly used subdivision scheme is temperatures of black bodies for which spectral peaks fall at the given wavelengths. According to Wien's displacement law, near an SWIR is sometimes called reflected infrared, whereas MWIR and LWIR is sometimes referred to as thermal infrared. Due to the nature of the blackbody radiation curves, typical hot objects, such as exhaust pipes, often appear brighter in the MW compared to the same object viewed in the LW. CIE division scheme. The International Commission on Illumination recommended the division of infrared radiation into the following three bands: ISO 20473 scheme. ISO 20473 specifies the following scheme: Astronomy division scheme. Astronomers typically divide the infrared spectrum as follows. These divisions are not precise and can vary depending on the publication. The three regions are used for observation of different temperature ranges, and hence different environments in space. The most common photometric system used in astronomy allocates capital letters to different spectral regions according to filters used. I, J, H, and K cover the near-infrared wavelengths. L, M, N, and Q refer to the mid-infrared region. These letters are commonly understood in reference to atmospheric windows and appear, for instance, in the titles of many papers. Sensor response division scheme. A third scheme divides up the band based on the response of various detectors. Near infrared, from 0.7 to 1.0 micrometers. Short-wave infrared, 1.0 to 3 micrometers. InGaAs covers to about 1.8 micrometers. The less sensitive lead salts cover this region. Mid-wave infrared, 3 to 5 micrometers. Long-wave infrared, 8 to 12 or 7 to 14 micrometers. Very long-wave infrared, dot. Near-infrared is the region closest in wavelength to the radiation detectable by the human eye. Mid and far-infrared are progressively further from the visible spectrum. Other definitions follow different physical mechanisms, and the newest follow technical reasons. Unfortunately, international standards for these specifications are not currently available. The onset of infrared is defined at various values, typically between 700 nanometers and 800 nanometers, but the boundary between visible and infrared light is not precisely defined. The human eye is markedly less sensitive to light above 700 nanometers wavelength, so longer wavelengths make insignificant contributions to scenes illuminated by common light sources. However, particularly intense near-IR light can be detected up to approximately 780 nanometers, and will be perceived as red light. Sources providing wavelengths as long as 1050 nanometers can be seen as a dull red glow in intense sources, causing some difficulty in near-IR illumination of scenes in the dark. Leaves are particularly bright in the near-IR, and if all visible light leaks from around an IR filter are blocked, and the eye is given a moment to adjust to the extremely dim image coming through a visually opaque IR passing photographic filter, it is possible to see the wood effect that consists of IR glowing foliage. Telecommunication bands in the infrared. In optical communications, the part of the infrared spectrum that is used is divided into 7 bands based on availability of light sources transmitting, absorbing materials, and detectors. The C band is the dominant band for long-distance telecommunication networks. The S and L bands are based on less well-established technology, and not as widely deployed. Infrared infrared radiation is popularly known as heat radiation, but light and electromagnetic waves of any frequency will heat surfaces that absorb them. Infrared light from the Sun accounts for 49% of the heating of Earth, with the rest being caused by visible light that is absorbed then re-radiated at longer wavelengths. Visible light or ultraviolet emitting lasers can char paper, and incandescently hot objects emit visible radiation. Objects at room temperature will emit radiation concentrated mostly in the 8 to 25 micrometers band, but this is not distinct from the emission of visible light by incandescent objects and ultraviolet by even hotter objects. Heat is energy in transit that flows due to temperature difference. Unlike heat transmitted by thermal conduction or thermal convection, thermal radiation can propagate through a vacuum. Thermal radiation is characterized by a particular spectrum of many wavelengths that is associated with emission from an object, due to the vibration of its molecules at a given temperature. Thermal radiation can be emitted from objects at any wavelength, and at very high temperatures such radiations are associated with spectra far above the infrared, extending into visible, ultraviolet, and even X-ray regions. Thus, the popular association of infrared radiation with thermal radiation is only a coincidence based on typical temperatures often found near the surface of planet Earth. The concept of emissivity is important in understanding the infrared emissions of objects. This is a property of a surface that describes how its thermal emissions deviate from the ideal of a black body. To further explain, two objects at the same physical temperature will not show the same infrared image if they have differing emissivity. For example, for any preset emissivity value, objects with higher emissivity will appear hotter, and those with a lower emissivity will appear cooler. For that reason, incorrect selection of emissivity will give inaccurate results when using infrared cameras and pyrometers.